Space-time is a concept that merges the three dimensions of space with the fourth dimension of time. This union creates a single interwoven continuum that is essential for understanding the universe. Together, these form a four-dimensional structure that is fundamental to our understanding of reality. This structure is not just theoretical, it has practical implications in physics and cosmology. In this framework, every event that occurs is marked by its position in space and time. This means that any occurrence can be pinpointed precisely within this four-dimensional grid. The significance of space-time is immense. It is the very fabric that holds the universe together, influencing everything from the smallest particles to the largest galaxies. It serves as the stage on which the events of our universe unfold. Every motion, every interaction, and every phenomenon takes place within this space-time framework. Without it, there would be no way to measure distances or track the passage of time. Our entire system of navigation and timekeeping relies on the principles of space-time. This interconnected fabric is what allows us to define and understand the physical world. It provides a consistent backdrop against which we can measure and observe the universe. To grasp the concept of space-time, imagine it as a vast, stretchy fabric. This fabric can be bent, stretched, and distorted by the presence of mass and energy. Any object with mass distorts this fabric, creating what we perceive as gravity. This distortion is what causes objects to be attracted to one another, a fundamental force in the universe. This distortion influences how objects move, leading to phenomena such as the orbit of planets around the sun. The paths of celestial bodies are curved due to the warping of space-time. Thus, space-time is not just a passive backdrop, it actively shapes the dynamics of the universe. It is a dynamic entity that interacts with matter and energy, playing a crucial role in the evolution of the cosmos. Atoms are the foundation of matter. They consist of a nucleus made of protons and neutrons, surrounded by electrons. These tiny particles come together to form everything we see and touch. Each type of atom corresponds to a chemical element. For example, hydrogen atoms have 1 proton, while oxygen atoms have 8. The arrangement of these atoms determines the properties of substances. When atoms bond, they create molecules, which are the building blocks of our world. The structure of an atom is mostly empty space. The nucleus is incredibly dense, but the electrons are spread out, creating a cloud around it. This cloud defines the atom's size and how it interacts with other atoms. Despite their small size, atoms are incredibly complex. They follow specific rules of physics, which govern their behavior. Understanding atoms is crucial for grasping the nature of reality, as they form the basis of all matter. Traditional atomic theory has provided us with a solid foundation, but new theories have expanded our understanding. One such advancement is the concept of quarks and gluons, the building blocks of protons and neutrons. Quarks come in different flavors, such as up, down, charm, and strange. These particles are held together by gluons, which act as the force carriers. The interactions between quarks and gluons are described by quantum chromodynamics, or QCD. Additionally, the discovery of the Higgs boson has deepened our understanding of mass. The Higgs field gives particles mass, which in turn affects how they interact with space-time. This discovery was a monumental step in particle physics. Another intriguing theory is string theory. It suggests that particles are not point-like but rather tiny vibrating strings. Each type of vibration corresponds to a different particle. String theory aims to unify all fundamental forces, offering a potential theory of everything. Section 4. The Puzzle of Quantum Mechanics. Quantum mechanics is a branch of physics that deals with the behavior of particles at the smallest scales. It challenges our traditional views of reality, introducing concepts that seem counterintuitive. One of the key principles of quantum mechanics is superposition. Particles can exist in multiple states at once until they are observed. This idea is famously illustrated by Schrödinger's cat, a thought experiment where a cat is simultaneously alive and dead until observed. Another perplexing concept is entanglement. When particles become entangled, their states are linked, no matter the distance between them. A change in one particle instantly affects the other. This phenomenon puzzled even Einstein, who called it spooky action at a distance. Quantum mechanics also introduces uncertainty. According to Heisenberg's uncertainty principle, we cannot simultaneously know a particle's exact position and momentum. This uncertainty is not due to measurement limitations, but is a fundamental property of nature. Section 5. Quantum gravity, the rules of the universe. In this section, we delve into the fascinating and complex world of quantum gravity, a field that aims to unify the principles of quantum mechanics with the force of gravity. Quantum gravity seeks to describe gravity according to the principles of quantum mechanics. This endeavor is crucial because, at the smallest scales, the classical understanding of gravity, as described by Newton and Einstein, no longer holds true. Traditional theories of gravity, like general relativity, break down at extremely small scales, such as inside black holes. These are regions where the gravitational forces are so intense that the fabric of space-time itself is warped beyond recognition. Hence, a quantum theory of gravity is needed. This theory would not only explain the behavior of gravity at the quantum level, but also reconcile it with the other fundamental forces of nature. One approach to quantum gravity is loop quantum gravity, or LQG. This theory suggests a radical departure from the continuous nature of space-time proposed by general relativity. It proposes that space-time is made of discrete loops, not a continuous fabric. These loops form a kind of quantum foam, a dynamic and fluctuating structure at the smallest scales. These loops are incredibly tiny, on the order of the Planck length, which is about 1.6 x 10 circumflex 35 meters. At this scale, the very concept of space-time as we know it changes dramatically. The structure of space-time becomes quantized, similar to how matter is composed of atoms. This quantization could provide a new way to understand the fundamental nature of the universe. Another compelling theory is the holographic principle. This idea has profound implications for our understanding of the universe. It suggests that the entirety of our universe can be described by information encoded on a two-dimensional surface, much like a hologram. This means that our three-dimensional reality could be a projection of this two-dimensional information. This idea arises from the study of black holes and their entropy. The entropy of a black hole, which measures its disorder, can be described by the information on its surface area, not its volume. String theory also contributes to the quest for quantum gravity. This theory posits that the fundamental building blocks of the universe are not point particles, but tiny vibrating strings. It posits that the vibrations of strings create the fabric of space-time. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. String theory's extra dimensions offer potential insights into how gravity operates at the quantum level. These additional dimensions, beyond the familiar three of space and one of time, could hold the key to unifying all fundamental forces. Section 6. Consciousness and reality. The relationship between consciousness and reality is a profound and complex topic. Some theories suggest that consciousness plays a fundamental role in shaping reality. One such idea is the observer effect in quantum mechanics. It posits that the act of observation affects the state of particles. This raises questions about the role of consciousness in the physical world. Could our awareness influence the fabric of reality? Another perspective comes from the field of cognitive science. Our brains create a model of the world based on sensory input. This model is our subjective reality, which may differ from the objective world. Thus, consciousness shapes our perception of reality. Philosophical views like those of idealism argue that reality is primarily mental. According to this view, the physical world is a construct of the mind. This challenges the notion of an external, objective reality, suggesting that consciousness is the foundation of all existence. Section 7 is reality external or internal. The question of whether reality is external or internally constructed has intrigued philosophers and scientists alike for centuries. This debate touches on the very essence of our existence and the nature of the universe. Traditional views assert that reality exists independently of our perception. This means that the universe and its laws are out there, functioning whether we observe them or not. However, certain theories challenge this notion, suggesting that our understanding of reality might be more subjective than we think. One argument for an external reality is the consistency of physical laws. These laws, such as gravity and electromagnetism, appear to be universal and unchanging. Regardless of our observations, the laws of physics remain constant. This consistency suggests an external structure that exists independently of our minds. This external structure is what many scientists believe forms the backbone of our universe, providing a stable framework within which everything operates. Conversely, theories like subjective idealism propose that reality is a mental construct. According to this view, our perceptions and consciousness define what we consider real. Our senses and mind shape our experience of the world, suggesting that without observers, reality as we know it would not exist. This view implies that the universe is fundamentally tied to our awareness and that our minds play a crucial role in its existence. Another perspective is the participatory universe, proposed by physicist John Wheeler. This theory suggests that observers are not just passive witnesses but active participants in the creation of reality. It suggests that observers play a crucial role in bringing the universe into existence. Our observations and measurements influence the very fabric of reality. In this view, reality is a collaborative process between the observer and the observed. The universe and consciousness are intertwined in a dynamic relationship. In conclusion, the nature of reality remains an open question. Whether it is an external construct or arises from within, our understanding continues to evolve. As we delve deeper into these philosophical and scientific inquiries, we uncover more layers of complexity and wonder. Exploring these ideas helps us grasp the profound complexities of existence, pushing the boundaries of what we know and inviting us to question the very fabric of reality itself.